Hey everyone, and welcome to this free course on my YouTube channel called Complex Analysis. Um, this is going to be a slight introduction to this course, um, and I thank you for joining on this exciting journey with me. Um, and complex analysis is one of the most fundamental, fascinating subjects in all of mathematics. It's used mostly in telecommunications and all sorts of building dynamic technology. So really complex analysis refers to a set in number theory called the complex numbers. And that set was not really invented, it was sort of discovered. So let's actually get into how complex numbers came about. So remember back in the quadratic formula, um, you had uh, this following equation, right? Ax squared plus bx plus c equals 0, right? And we can actually use the quadratic formula to figure out the roots of a quadratic equation, right? X equals minus b plus or minus b squared minus 4ac over 2a, okay? And the number of solutions in a quadratic equation comes from this quantity, which is called the discriminant of a quadratic equation. If b squared minus 4ac is greater than 0, there will be two distinct solutions, okay? If b squared minus 4ac is 0, then there will be one repeated solution. However, if b squared minus 4ac is less than 0, there is no real number uh, solution to this quadratic equation. So we'll get actually two complex roots. And this is short. And the next one is just giving you an overview of the derivation behind the quadratic formula. And you're just using the complete the square method. So what uh, this proof is saying here is that you factor out the A quantity uh, to look like A times x squared plus B over AX for the first two terms, and you leave the constant C by itself. Okay. And then uh, this right here, this next line, I'm using the square method. So we add b squared plus 4a squared, and you subtract that same quantity on both sides to get the equation balanced, right? And so you'll end up in this form. And then from here, you're just solving for x. So solving for x would give us a times x plus b over 2a squared equals to b squared over 4a minus c. And if you do a bunch of algebra, you will eventually get to this quantity right here. If you square root both sides, x plus b over 2a is equal to plus or minus the square root of b squared minus 4ac over 4a squared. And thus, this here's the quadratic formula, right? Minus b plus or minus this quantity, let me highlight this properly. This quantity, that's the discriminant, b squared minus 4ac over 4a squared, okay? Um, and then just for fun, I might, yeah, I'll go over this one, yeah. So we can look at the how the solutions look like graphically. So let's see if I can go to this link here. Great. So if I go to another screen, let's see. The wonders of technology, right? So here is what the solutions look like on Desmos. Graphically, well, it's a parabola, but this right here, this would give us, so if I type in b squared minus 4ac in this box, this would yield a negative discriminant. So that would give us a complex solution. So if you have a negative discriminant, that would give us a graph that does not cross the x-axis, right? But yeah, we'll change grade. So if I just change the C value just a little bit and yeah, make it look like this. The discriminant is positive, right? Which means we will have two roots here that cross the x-axis. So this point right here and this point right here, okay? And cross the x-axis. And if the C, if I just do this very carefully, if I can make it 0, right about two of, okay, I gotta do this very carefully. Let's see, shoot, okay. Well, if you look at very, very closely, maybe I'll get up to 0.33, see what that happens. Minus 4ac. You had to do this with very good precision. So, oh man, okay. So, yeah, so about 0.41. If you let that to be C, you'll eventually get b squared minus 4ac equal to 0, right? And you'll have one repeated root in the quadratic equation. So really part of complex numbers was discovered, well, just looking at the quadratic formula. And then really it goes back to going back to the early 14th century, right? So so here, oops, so it actually started off with the early 14th century with Niccolo Tartaglia and Girolamo Cardano. Sorry if I'm mispronouncing that wrong. So, and it was later refined by Raphael Bombelli in his book, Lie Algebra, by his book. But really, it all started off with solving this form of a cubic equation. X cubed is equal to some number, p times x plus q. P times x plus q. So p and q are real numbers. And really, it's so Tartaglia and then Cardano were mathematicians that were on a quest to figure out what the different solutions are to this form of a cubic equation. And then it led to Cardano deriving his own formula called Cardano's formula. I know it's going to be pretty lengthy to write this type of solution out on this window, but let me do another screen. So it actually goes. So actually, let me erase this so that everyone can see it. Okay. So Cardano's formula. So this right here, this was Cardano's formula. And then the problem was they looked at different values for P and Q. So, and it was a big, it was a big event in the early 15th century when they derived solutions to the cubic equation, right? AX cubed plus BX squared plus CX plus D. But a really good so a really good sorry so a really good example on where complex analysis comes in. So it actually looks at this example here. So so if I look at this equation, 6x plus 4. That's where, so if we look at this example, that's where Cardano's formula breaks down, because you'll have numbers which will have negative square roots. And that was the formulation of where complex analysis came from. So it all started off with Cardano's formula, formulated first by Tartaglia and then Cardano. And then the solution was published for cubic equations in Bombelli's book. And then there was also further contributors to complex analysis, including, of course, Euler, and then William Hamilton was also a big contributor to looking at different different complex functions and conformal mappings. And also another one was Augustin Louis Cauchy. So we'll look at functions in the complex number plane, the complex plane, and we'll look at when functions are analytic. And we use different equations which were derived by Cauchy, called the Cauchy-Riemann equations. Okay. Bernard Riemann was another contributor to complex analysis too. This Hamilton, I think he was part of the residue theorem, so he was part of that too. So nevertheless, so anyway, complex analysis is really cool. I actually like this subject in math, so and I'm really excited that you are part of this journey with me. So the textbook that I'm going to go over, that I'm going to use in this course, is the first course in complex analysis by Dennis Zill and Patrick D. Shanahan. I'm using the second edition of this textbook, and this is the textbook that I used when I took this course. So it's really good. It has a lot of exercises, different application problems, and I'll list out those problems for you to work on just to check comprehension. And I say every math is super important for this course, but the prerequisite is if you have taken either Calculus 2 or Calc 3, you should be okay, right? You should tackle most of the content in this course and the problems listed in the textbook. Yeah, Calculus 2, we'll go over different types of Taylor series in the complex number system, and then we'll look at Laurent series. And then Calc 3, we'll deal with line integrals back. We'll deal again with line integrals, what it means for a vector field to be conservative. So you don't have to know that in this course, but I think it's good. It's a good thing if you have taken at least Calc 3. You'll be able to work on the problems here in this course. So let me actually erase this. I don't need that. And then finally, this is any course in college is a commitment, especially this one. So it's, if you want to be successful, you want to make sure you follow along with the videos that I post. At the end, I'll list out problems for each section for you to work with, just to check comprehension. And all of math is not easy, especially complex analysis. It was a pretty hard course for me. So there will be times that the material may seem overwhelming, it will become difficult, but always remember to believe in yourself. If you do that, then you will go a long way, right? In math, especially in complex analysis. So if you're ready, let's get to learning complex analysis. I'll see you in the next video.